Hello! We are going to be making some videos. So we're going to be starting here in chapter 1.1 to section 1 or section 1.1 to 1.4, and we are going to be talking about stress. So we're finally starting strengths, and we're going to be looking at normal stress under an axial load. So a lot of what we're going to be learning it's just vocabulary, and you're just going to have to put the definitions inside your brain, so that through the semester, when I say an axial load, you know that it's a normal stress. It's going through the axis, okay, that it is perpendicular to that cross section. So let's just get started on some of those vocabulary words. So, not changing. Okay, so what is stress? Stress is an intensity of internal force. It is force over cross-sectional area. Okay, that's the units. It's like if you pump up your tire and you pump it up to 15 psi, pounds per square inch. Stress is a force per unit area. Okay, when we talk about stress, there are two types of stress that we're going to talk about. The first stress is a normal stress. Normal stress means perpendicular to that plane. So whether the plane is cut like this, okay, normal is always perpendicular to that plane that I'm looking at. Shear is always parallel to that plane. It doesn't matter where the plane is, how I want to cut the cross section, okay? I think of shear like a loaf of bread. When I'm cutting through that loaf of bread with my knife, I am shearing that material. I am putting a force that is parallel to that cross section as I cut down. Well, also when we talk about deformation, shear deformation, when I cut that bread, it makes like this nice little angle change. When I look at normal force, it's a pushing or a pulling, a pushing or a pulling. It's going to be a change in length. So they both are going to have force per unit area, okay? But they have different behaviors in terms of when I apply a loading, what's happening. But normal, perpendicular, shear, parallel, tangent to the plane, okay? And the normal force can come from other things. So we're going to start in chapter 1 and 2 and 3 and 4. And we're just going to look at axial loads. That's like if I have a rubber band, which I had a rubber band out, okay? This would be, that's an axial load, okay? And you can see that change in length, okay? When when we do beams, which is way back in chapter 6, I thought I had some post-it notes here, but when I look at a beam and I bend a beam, then we can see that these fibers at the top are going to have to smush, have compression to make that curve. These fibers at the bottom are going to have to elongate to make that curve. So even when we look at moments, okay, we'll have a normal stress from bending because fibers are shortening and lengthening to make that curve happen. That's chapter 6. So normal just means we have that change in length, okay? It's acting perpendicular to my cross section. It can come from a normal force, an axial load, or it's going to come from bending. Like here's my beam, compression, tension, okay? Shear, again, shear is like this skewing. It's a parallel surface force, okay? It's like slicing that loaf of bread. It has a distortion. Okay, so if I had a perfect rectangular loaf of bread and I went to slice it, the top of it goes down like that. We can see there's this angle change. That's the shear deformation. But at the end of the day, it's normal, shear. Those are our two types of stresses that we have. So units. This class, again, it's not a lot of fancy formulas like you're going to have in thermo or fluids. It's honestly, we have forces, we have lengths of beam, lengths of cross sections, and we have force over area, okay? So it doesn't matter when we look at bending stress or normal stress or torsion or beam shear, it's all going to be stress, force over area. Our equations will look different, but the units are always going to work out to force over area. PSI, KSI, Pascal. So when we're looking at cross sections, we'll have to make sure that if we're given cross sections in millimeters, that we put those into meters. And if I'm given moments, okay, when we get to bending moments, if I'm given a bending moment of kip feet, okay, I'm going to have to make sure I put it into kip inches. because our units are PSI, KSI, and Pascal, Newton per meter squared. If you don't know which direction to go when you're working problems, your units will they'll take you where you need to be. Okay, so what is a normal stress from an axial load? Okay, what is normal stress under axial load? It's anything that's going to be a two-force member, tension and compression. It's going to be members in a truss. It's going to be columns. It's going to be cables. It could even be a bolt. If we are tightening a bolt, okay, the reason we have a torque wrench is so that we only tighten bolts so far. There's lots of things that can go wrong if we over tighten, but one of those things is as we're tightening that bolt, it's actually pulling it, like we're tight, it's causing tension, and you can have that bolt pull apart in tension. So we have to start thinking about all the ways that things could go wrong, okay? All the ways, because there's lots of ways that our structure could have issues, okay? But all we're going to be looking at right now is normal force belts. If you're a mechanical engineer, I mean, they're in tension, okay? You tighten things up. It's just anything that has a normal force, which is perpendicular to the cross section. It's an axial force. It's acting, we assume, through the axis. So our first equation we have in strengths is stress equals N over A. Remember I said stress is just a force over area. When we cut that beam in statics, we found normal, shear, bending moment. There's torque on there also. And that's the normal force we were finding in statics. That's it. So if I know the cross section of my member now, I know it's a cable with a 1-inch diameter. Force over area, that internal normal force divided by the cross-sectional area gives us our normal stress. Now the important thing right here to look at is that our normal stress under an axial load is a sigma. Sigma means normal stress. When we start looking at allowable stresses, we will have normal stresses and we will have shear stresses, okay? Normal, shear. Normal means change in length. Shear means kind of that skewing of the cross section. When we do a beam and bending, remember I said it's going to have a normal stress because really we have changes in lengths of those fibers. It'll have a different equation, but it'll still be a sigma. It's still a change in length. Normal stress is a sigma. Shear stress is a tau, and we'll get to that in a minute. So I have normal stress. Again, axial means along the longitudinal axis, and we assume that it's acting right through the centroid, because if it's not acting through the centroid, if it's offset, it's creating a moment. So we're just all of our forces right now, they're axial through the axis, through the centroid. Axial, longitudinal, perpendicular to my cross section. So if I have a system here, I have an external force. It's an external force that's perpendicular to the cross section. It's acting along the longitudinal axis. It's acting through the centroid. That is an internal normal force, right? So if I were to cut it at A, okay, if I were to cut it at A and draw a free body diagram of from the bottom with the force P and A, the internal normal in, I would also have shear, moment, and torque, but we can see we don't have those. It's just in. I can actually find that internal resisting force, and we've been calling that in. It is perpendicular to the cross section. It is a longitudinal in nature, and it's acting right through the centroid of the cross section. Okay, so it's the equal and opposite. It's the equal resisting force internal to the outside external applied force. External, internal, equal and opposite. That's just in. You all know how to find that. So what is stress? Stress is that internal resisting force in divided by the cross-sectional area. Okay, and we call it a stress average because we're going to assume that each individual point on that cross-section is undergoing the same amount of stress. When I stretch my rubber band, okay, when I stretch my rubber band, I'm applying, it looks like I'm squishing it, but I'm holding it and I'm pulling. See, my forces are going this way and that way. Okay, so I have to assume if I could look at the cross section of this rubber band, that if I were to cut it, find internal, that each little tiny piece of the rubber band has the same amount of stress. Okay, it's just an average. So it's just that internal in, which we've been finding in statics, divided by cross section. Easy peasy. Okay, so why is it important that we used positive beam notation? because I have to know whether something's in tension or compression. Because if I'm working with concrete, they behave differently, whether we're in tension or whether we're in compression. They have a different, they might have a different behavior. Concrete's very, very strong, very, very strong in tension. I mean, in compression, not so strong in tension. Okay. So I always assume a positive internal normal, positive, positive, positive. Okay. It's tension behaviorally. If I get a negative using my statics equilibrium, I know I'm actually in compression. And this is important because now my stress can be positive or negative. If I told you it was a positive normal stress, then you know it's a tension member. If I told you it was a negative normal stress, then you know it's a compression member, like a column. If I ask you to draw on the cross section how the stress is distributed, we said it was average, so it's just going to look like a square. Okay, where all of these fibers are experiencing that same amount of stress. If it's in tension, arrows up. If it's in compression, arrows pushing back on the cross section. We could also say to you on an element, on a block, on a stress block, draw the stress. So if I were to take a little teeny tiny rectangle off of that entire cross section, then I would show tension stress, compressive stress, and put a value. And this is going to be important as we move to the end of the semester and we start putting all of our stresses together, because then we're going to rotate it. It's going to be lots of fun, but we have to know how to draw a stress block. Okay, so positive, we assume it's positive. That means it's in tension. It's going to be elongating. If we get a negative normal, that means it's a compression. It's shortening. If I ask you to draw on the cross section how the stress is distributed, it's the same. It's like a square. You know, it's all, everything has got the same stress. It's an average. And if I ask you to draw it on a stress block, it's literally, I'm just going to take a little tiny block out of there and just show you it's tensile stress or compression stress. So a lot of what we're learning is vocabulary. Procedure for analysis. I call these cake problems because if you imagine it up, it looks kind of like a wedding cake with different tiers, okay? If we want to find the internal normal stress in each of these segments, if we put these loads up like a shear force, you guys would know exactly where I needed to segment to write my equations. For some reason, when we turn them sideways and make them normal in direction, students go like, wait a minute, what just happened? Okay, just pretend they're like shear, you treat it the same way. So I can see that at A, I have 12 kilonewtons pulling to the left, and nothing changes until I get to B. So it doesn't matter where I slice it between A and B, it's going to have the same internal normal force. At B, I have this collar, and we're applying a 9 above and a 9 below. And that's important because we're not creating a moment, because they're both counteracting each other. So it's essentially like there's 18 going through the centroid. Okay, so then nothing from B to C, it's all going to be the same. Up at C, I have another collar. I'm adding more axial loads. So I can see I'm going to have an A to B, a B to C, and a C to D segment. And I'm going to approach this the same way that I would for shear. Okay, so if I have 3 segments and I'm writing equations, how many free body diagrams am I going to have? I'm going to have 3. And this is where, take your Post-it note, cover up either everything to the left or everything to the right. Okay, so number 1, draw a free body diagram. So I'm going to cover up, I'm going to cut it between A and B, and I'm going to cover up everything to the right, and I'm going to draw my free body diagram. There's my free body diagram. Okay, there's my free body diagram. I know I'm going to have a segment from B to C. So I'm going to take that Post-it note off. I'm going to move it down, and I'm going to cover up to the right of B to C. And I'm going to draw my free body diagram. It includes everything up to that point. It's just like a beam. You can't just take something out of the middle and call it a day. You have to include everything to the left or everything to the right if we're looking at equilibrium. Okay, and I have my internal normal. I'm assuming it's in tension. I don't know. Okay, tension. My next cut, C to D. I'm going to cover up everything to the right, just like I have been, and I'm going to draw my internal or my free body diagram. It shows everything leading up to that point. And I have my normal force assumed in tension. I'm always going to assume tension, because if I assume it in compression and get a negative, I may say, oh yeah, see, it's negative, it's in compression. No, if I assume it in compression and it's negative, it means it's really in tension. It's the opposite. So always assume it in tension. If you get a positive value, tension. If you get a negative value, compression. You don't have to think about what you did, okay? So then I can use equilibrium. This is the statics part still. It's just statics. And I can sum my forces in the x direction equals 0. So my first equation would be negative 12 plus NAB equals 0. NAB equals 12. My second equation would be negative 12 minus 18 plus NBC equals 0. I would find that we have 30. And then 12, 18, positive 8, positive NC, because I'm using to the right is positive. And now we have our internal forces. So I could actually draw an internal force diagram, just like we did a shear diagram, and see how it changes. Okay, if I want to find the stress, I have to determine my cross-sectional area. So that's probably given to me. Okay, stress is just internal force, 12 kilonewtons, divided by cross-sectional area. Internal force, B to C, 30 kilonewtons, divided by cross-sectional area. And make sure you're checking your units, because normally our forces are in kilonewtons or newtons. When we divide, we need to make sure that we're in meters for a cross-section so that we have Pascal as the answer. Check your sign convention. If I'm in tension, my stress will be positive. If I'm in compression, my stress will be negative. So that if I told you it's a negative 35 KSI, you know it's in compression. Okay, you know that. And if you're ever confused on an exam, they gave me a value. If it's in KSI or Pascals, it's a stress that we gave you. If it's in Newton or pounds, it's a force. This is all we have. We don't have anything fancy in this class. You need to be comfortable solving problems forwards and backwards. And you're going to find on your homework, sometimes you're given load P and you have to calculate this. Sometimes you're going to be given this and you have to calculate load P. Either way, free body diagram, find reactions in terms of P or in terms of the forces that are given, and then work on your stress, okay? So this would be the force diagram. Here's my internal force diagram. Everything was in tension, and so I can show you from A to B, it's 12. Because this bar looks like it's a uniform dimension all the way down its length, it looks like it's all the same material and it's all the same width and height, then if I were designing this bar, I would know that B to C is my limiting section, and it has a force of 30 kilonewtons. So I would have to use that 30 kilonewtons to design the entire bar, because that's where I'm going to have, that's where the highest internal force is. It's going to be the highest internal stress. That's where I have to determine my failure from. Okay. Why is all this important? Because we don't want failure. Like, we don't want failure. And you can see this bolt over tightened, normal failure. You can see the necking. If you've taken a material science or you're taking the strengths lab right now, you can very clearly see the necking of that material before we failed. Okay. And we'll talk about materials in a couple of weeks. The other thing that I want to note is that failure doesn't always mean that something has just completely fallen apart. Okay, this would be catastrophic failure. That column, pretty catastrophic, right? Sometimes failure just means maybe we've exceeded a tolerance. If you have a mechanical equipment and you have little tiny wires in your equipment and little tiny gears, think about it like a watch, like a Swiss watch that you can see with the gears. Sometimes if something elongates just a little bit too much, we have too much stress, we have a little bit of elongation, it's not failed, but our tolerance doesn't really allow for it, so the whole thing is gunked up. Okay, that would be a serviceability failure. That's a serviceability failure. It kind of goes back to if you're on a second floor of a mall and you've all walked around the little walkways and you can feel those vibrations. Okay, if it vibrated more than what it did, people might be concerned, even though structurally it's sound. Okay, so sometimes things are failure because it's a serviceability issue that people aren't comfortable. Okay, and that's where when we talk about failure doesn't always mean the bolt is completely ripped apart, but it could be elongated just enough that there's now play in my system and it's not behaving the way that I thought it should. Okay. So another thing about strengths a lot of students have a hard times with is that a lot of times it's story problems. And everybody's like, I don't want a story problem. You have to be comfortable with going through the story problem and picking out what you need. Okay, so let's just start. I have a stainless steel tube. Okay, what is a tube? I'm gonna draw a cross section of a tube. Okay, because I'm working with a tube. It's not solid. It has an outside diameter of 60 millimeters. Okay, I have an outside and a wall thickness of 5. Perfect. Okay, here's my tube. Here's my outside diameter. Here's my wall thickness. So if I know that I have to find area, area is pi r squared. If it's a tube, it's going to be pi r outer squared minus r inner squared. Or I could do pi over 4 d outer squared minus, well, I don't have an inside radius. How do I get the inside radius? How do I get the inside the inside diameter is the outside diameter minus 2 wall thicknesses. And I can see that because I have a cross section that I drew. Okay, it's used as a compression member. Aha, it's like a column. It's in compression. So my stress is going to be negative. Okay, so if it's a material that has a different behavior, whether I'm in tension or compression, I'm going to have to make sure that I'm getting the compressive stress value out of a table. It's telling it, oh, it's an axial stress. That means it's truly pushing down like a column right through the centroid. I don't have moment, I don't have shear, I don't have bending, okay, from or torque, and the stress has to be limited to 340 megapascals. Again, if I knew what material it was, I would have to go look it up in a table, okay, because when you have a job, they don't just give you everything you need. You might have to do a little research, and that's where it's important to understand that it's a compression member. So if my material has 2 different values for normal stress, tension, compression, I'd have to pull the compression limiting value. Determine the load P. So, okay, it's axial stress. P over A. That's my axial stress. It's actually negative, so negative P over A. I have a limit of 340, and I have a cross section that's given. It's not a convenient way that it's given. I can calculate P. And that's where you just maybe take a highlighter or underline what it is that's important. And so I know that it's stress equals P over A. I know it's a normal stress because it's in compression and it tells me it's axial. Okay, and then I have to go through like what am I given? And we're not going to go through these. It's you can look at them on your own, but I work through it and you can go back and look at it. Okay, here's another axial problem, and you guys have access to these in your slides, I believe. If I have axial loads given, determine minimum diameters. Okay, I have to cut it like a cake and find all of those internal forces. That's a lot of free body diagrams. That's 3 free body diagrams, 3 sets of equilibrium equations to find in. And then I have different materials, so they all have a different stress, and they're all going to have a different diameter. And so, again, it's just working through what you know. You have to be able to go through and set up free body diagrams and find those internal forces before you can start the problem. Okay, so I'm going to start some examples now. I would say read your text. The next instructional video is going to be over shear V over A. We're going to be looking at shear caused by a normal force, which is going to be like a lot of bolted connections. Anyways, make sure that you're reaching out if you need some help and look for those videos.